Welcome to this tutorial. So it's about non-IID learning. It's very early morning. Okay, so welcome. So this morning, so myself, so Longbing, Tao, and the third person, the Guangsong, will be here to present this tutorial. Facebook cannot make it, and Chen Zhang is still in Sydney. So you're welcome to download the slides actually from this. There's a link here. It's just updated this morning actually. But the slides actually you will find actually many more pages than what we can do here, and cover a lot of more content than what we can present here within 3 or 30 minutes. So first of all, certainly this is a long time work by the whole team, not just by myself as a supervisor. I've got many students already graduate, and currently quite a few students still work on this. As you will see, work on quite a broad area and topics. So as I said, all of the slides can be downloaded here, and the relevant papers from us can be downloaded from the website here as well. So this is roughly what we're going to introduce today. So basically, the non-IID learning. So I'm going to introduce the concept of non-IIDness and also explain the issues with current IIDness or IID assumption. And we will now introduce the work about related work. I'll leave it to you guys if you are interested in some of them. I've got the slides online or covered some of them already there. And we'll now introduce non-IID data preparation. So those marked in red actually will be introduced here. So then we will introduce the non-IID representation. So that cover metric learning, similarity-based representation, and embedding-based representation as well. And we will address the issue of non-IID feature engineering as well, but not in a separate session. Mainly in some of the sessions we'll talk about like noisy data, redundancy data, and also high-dimensional feature engineering by considering the non-IID characteristics. We'll also introduce some of the work related to non-IID recommender system. So we'll present a non-IID recommender system framework and also introduce one of piece work about the session-based recommender system by considering some of the non-IID characteristics there. And we'll also introduce non-IID outlier detection. And then another topic is about non-IID behavior analysis, and that actually behavior analysis is quite a popular topic now. And so we particularly focus on global-based behavior modeling. And we will also briefly introduce a piece of work about non-IID for vision learning. And before we conclude, we will just briefly review. So as you can see from here, it's quite broad today and cover quite many areas. And certainly this is also just a preliminary work in this area because non-IID actually is quite complicated. But we are, in the past 10 years also, we have been dedicated ourselves to this particular topic. So before I introduce the specific areas, I'd like to give you some brief overview in case some of the areas you are interested in and we couldn't cover here. This is a bigger picture about non-IID learning, and certainly we have been working on this IID data, IID assumption for many years. And for this non-IID family, so I think we can cover many things like non-IID signal processing, non-IID vision learning, image processing, outlier detection, clustering, feature engineering, statistical learning. By the way, today I will also briefly introduce some of our work in the statistical learning as well. And also non-IID ensemble, I will also briefly introduce the example here as well. So, so non-IID clustering, I will not introduce it. We have done a little bit of work in this area. And certainly it is all about non-IIDness of data. And as I said earlier, so we'll introduce non-IID representation in terms of like embedding, matrix learning, etc. And also non-IID model system. We did some work on rule learning, especially pattern relation learning, by considering non-IID feature, but we will not introduce here. It's online in the website. And some of my students actually have been working on topic related to incorporating the non-IID features in the network data, in the social media, social network analysis. And we will briefly introduce the non-IID behavior analytics as well. So there are many other opportunities actually in this non-IID learning system, but we are just going to cover some of them today. So some of the areas, just for your information, so you can find these from the slides which is available online, and you can also download the paper here. So in the past 10 years also, we have been sort of about issues about these conceptual issues like what is non-IIDness. And there's a concept in the statistical community about non-IID data as well, and there's another group actually work on what is it called beyond IID. And so we have been thinking about this topic and about non-IIDness, particularly about the complex relation, what we call a coupling relationship, and the types and the forms, the hierarchical things, and the challenge of this coupling learning as well. And in the pattern mining as well, and we think about how we can actually better understand the object relation and the pattern relation, even though frequent pattern mining may not be so useful in business as far as my experience told me. And work on more complex data, that actually could combine different patterns. And the data representation, so actually cover more than that. And there's a list of work with EJK actually talk about embedding-based representation with hierarchical value coupling. So I will introduce this later. And the data discretization, so we also actually consider this non-IID characteristic in the data before we discretize the data. And the k-means, so we will show you actually can change k-means by considering the complex relationship there in the data. And certainly we can also use that for like some other clustering method like spectral clustering, etc. And also for the classification, like for KN and for different kind of data characteristics, like for multi-label or for noise data, for the considering the further information or imbalance data. So that's about those basic area, and also later today I will also introduce a little bit about this ensemble clustering. So when we do the ensemble learning, so what can we do to improve and to address the issues that may cause in the current ensemble framework. And so we have been working a lot on this behavior and what we call behavior informatics. There was a tutorial organized with EJK some time ago, actually particularly talk about behavior representation, modeling, reasoning, learning, analytics for individual and for group behavior. And today we actually will just briefly introduce group behavior, and by considering the complex relation there for one person's behavior or the relation between the group's behavior. So, and then there are some other work we did on the image processing, and by considering the relationship of heterogeneity in the image. And later this morning, I will introduce a piece of work with triple AI about the vision for image segmentation by considering the non-ID features. And then, so that's about the computer vision. And the statistical relational learning, so I'll introduce some piece of work we did in the current statistical model, and by considering some of the features related to dependence, related to the feature interactions, and etc. And we'll also particularly address outlier detection, and that actually will also address the feature relationship for the noise feature, high dimensional feature, and also the redundant feature design in the unsupervised way. And then this last piece about the pattern relation and the rule relation, and when you have many rules and many patterns, how they interact with each other, and how can we consider their relationship, and and to come up with more meaningful patterns, more actionable patterns, those kind of things. And recommender system, so a lot of work has been done in the past regarding this recommender system, particularly in the community, a lot about the cross-domain transport, etc. So my team and myself, and we have been proposing a framework called a non-ID recommender system framework. So I will introduce it here today, and then we introduce a piece of work, how can we handle MF-based recommender system by considering some of the non-ID characteristic, and some other work about session-based recommendation, as well as just accept the ZCO in EGKI. And then finally, so we will also, we have been also working on document analysis, considering the term relation, the term pair relation, and some other work has been published for the, in this area by, integrating with embedding with, more sophisticated, representation technique. And keywords query, so we didn't actually use all of the papers we have, but we are updated later. Sorry, I just realized still quite a bit of papers we haven't put here. So in the keywords query, actually, we, so consider the relation between the keywords and in the query, and how we can improve them. So that's roughly the progress review, and you can see actually cover quite many areas and a lot of people about some preliminary result in this area. So, so we all know, I guess, about the NIID learning, and that has dominated the our research and application and algorithms we can find in our domain, KDD or machine learning, CVPR, statistics. So let's just motivate ourselves, look at this example actually. Some of the search, from the one of the biggest search engine website actually report some of the news about a few years ago, some of the accident happened in Greece, and they needed to push advertisement help. So what is advertisement? This engine actually recommended to us. So this is recommendation. So we encourage everyone to go to Greece, and so I don't know how many of you guys would go there. But if they pay us, maybe, I don't know. Yeah, but anyway, so I think the key part is that to think about. So why this, this kind of recommendation was made by such a famous, it's almost dominant, website, search engine. This is the search engine that we use every day. So why, recommendation was made like this? So I think there could be many reasons. There could be, business reasons we couldn't control, like because of money, right? Because that particular place actually pay them. But so we actually think about it from the algorithm perspective. I guess, the engine actually just was driven really by by algorithm behind rather than by human. And if that is the case, one of the reasons we will think about maybe related to this IID, but sadly we don't really know. And because recommender system is a big issue anyway. So think about actually there's a relationship between the different piece of media and the content there in this early on in the news and in the picture, right? So do this recommendation needed to link this to the content here and to the text, right? But what is the relation between them, and how this model actually captures such kind of relation, and also the heterogeneity as well, because this image and this text and this is the image, there's different things here, and how the model could do better. So that I think we need to cover relationship and also heterogeneity, and this kind of relation could be quite interesting. Look at from the syntactic or semantic and from many perspectives. So if we just simply summarize and use empirical observation about this IID assumption, we have been taken advantage for a long time. So what would be this learning problem? So we've got a learning boundary here, and the different heterogeneous objects here, and this could be objects, could be methods, learners, could be like data source, and could be your learning results like patterns or like class labels, etc. Right? So just to treat all these as objects, right? Similarly, we've got three objects: O1, O2, O3. And then there are different kind of relation between them. So I just use some of the, a line, dash line, or whatever. So the line here shows there's different kind of relation between them. So this usually would be, the problem we usually face. Doesn't matter whether the data is big or small, right? Even very small data, just a few like transactions, this could be quite heterogeneous, and there could be this or that kind of relationship there, right? So what we usually do is to do a projection and to do based on assumption that those three objects or whatever they are, and they are identically distributed. So I just use the same shape to represent them, which means they are homogeneous, they are identically distributed. So then the second thing so we usually say, so they are independent, right? So I just ignore the interaction there, right? So then from the analytical and learning perspective, what do we need to do, right? So what we need to do is usually we have to build an objective function for this D3, this D3, and to calculate the distance between O3 and the baseline O, right? And when we calculate this D3, is a so-called objective function or whatever, cost or loss function, and we actually get this distance D3, but when we do this, we actually treat O3 to be independent from all other objects O1, O2, right? And we also actually ignore the impact of O1, that could be, there's a relation or significance or whatever, from O1 to O3, and similarly for O2, right? So basically we just have this simple, objective function, right? Okay. So this assumption assume the objects they are independent, and assume they are identically distributed, and then put together is so-called IID, and I just make this as a norm called IIDness. Does it make sense? Okay, so then let's look at some very typical popular algorithm. So some of people use in industry every day, I guess. So let's look at this. This actually is capital market data, tick data from a major stock in China actually. So the tick data, the people actually trade there, trade the different stocks at different times, the stock at different points with price, volume, etc., and directions, and And so if we do a few things here, like we commonly do with when we are given data, so we can do that. Okay, So we can do like association, frequent pattern mining to find the frequent trading patterns there, and then we can design a trading strategy, right? So called it algorithmic or high-frequency trading. And then we can also do the clustering and to understand, who in the market actually, they sort of like collaborate with each other or they got similar trading behavior. And certainly we can also do things like a classification, right? So we classify them and then, to find some like, short-term manipulators or insider trading, etc., right? So we just look at all these three. We just use a typical, the very popular, classical algorithm to do this. So what would be the assumption? So we usually say, okay, traders, you guys are independent, but is that true? We know that's not true, right? And then see, okay, behaviors of one trader actually is independent from others, right? Is that true? We know in capital market that's particularly not the case, right? So I personally have been working in this area for many years, more than 10 years. So I understand that's not really the case. And then we just look at one of the algorithms for clustering. For example, so what is the typical one is the k-means, right? So if we look at the k-means, so this is the objective function. So if we look at the objective function and say, okay, this xj is one of the objects pair, and you got the mean is of the k objects, right? And then we calculate the distance between the xj given objects and the mean of a group, and then to minimize this, and then say, okay, whether xj belong to the same group or different group. And now we can say, okay, so this is within the group, every object you get the shortest distance compared to to those objects in another group, right? And so that's basically k-means. So is k-means IID or non-IID? So if we look at this objective function, is this IID or non-IID? So we say, okay, so xj, so basically when we calculate this, xj is independent from others, right? But how about if xj actually, for example, we got two xj, xj1, xj2, which means the two objects pair. Two objects, they are dependent, on each other. Can we still use this formula, this objective function? Right. So obviously we cannot do it, right? So but you can still do it. If you still, use this one, so what could be the case? So outcome could be, misleading, could be wrong sometimes, right? So that could be the scenario. And if you look at it, Friday saying similarly, there's got a problem there, got an assumption there, right? So let's look at why k-means is, the current k-means are IID, the basic k-means is IID. So I explain a little bit because the xj do not consider interaction with all other objects, right? So in the objective function pair, and then so we have basically opted IIDness assumption. So assume UI for any cluster follow the same distribution, right? But this is a global, clustering issue, right? So there are some other issues. So I think mainly is that okay. So xj is independent, and xj1, xj2 they follow the same distribution. But actually we know that in the real world often we have to consider that actually this distribution could be quite different from another cluster, right? So then let's look at another one. So it's a typical classification models like decision tree or KNN. So similarly, if we look at a decision tree or KNN, it's got the same issue here, right? So same assumption here. So we can actually go through many other typical algorithms, and also some of the statistical method as well, and we have to look at the assumption. So that's the issue may actually be triggered by this idea assumption that sometimes we get the data, if we are lucky enough, okay, good, yeah. So the outcome is quite close to the reality, right? And then for some other data, not really, a little bit far, and some other quite far, right? So the issue here could be like, okay, so we based on the this DI, whatever matrix, right? So you use this matrix to do decision making or make recommendation to the senior executive. So what we have is that, okay, maybe we say anything below 4 will be low risk, and 4 to 6 or 4 to 8 will be medium, and then anything above 8 will be high risk. So for this example, say, okay, based on this recommendation, we say, oh, okay, it's fine, don't worry, because this is low risk, right? But actually it's on the boundary, right? So actually it's on the boundary. But for this particular data, this is all USI data, by the way. So for this particular data, you will find actually, by the way, don't do that, So it could be very risk because actually it could be high risk, but the recommendation here actually is low risk, right? So sometimes actually this could be quite dangerous. So I realized this problem actually more than 10 years ago when I worked with some of the big organization. We realized we can't really apply existing algorithm directly. We need to have a deep understanding about the data characteristic and also the assumption of the model. And particularly there is one thing here is called IID or non-IID. So then we started to think about what is IID and what is non-IID, and what is non-IIDness. And so that's a basic concept here. So it's basically two things. So one is that it's not identically distributed, and it's not independent. We put together called a non-IID, or you put a non here is non-IIDness. If that makes sense to you. So what is not identically distributed? Actually, you can also use another term for heterogeneity. So the heterogeneity, interestingly, what do we find actually? The heterogeneity could happen on the data type, attributes, the data source and aspects and formats, structure, distribution, the relationship, and even the learning results. And another term is not independent. So it's something what we call coupling relation. So we know in cybernetics, in statistics, we have this term coupling, right? Used in those areas. And so I explain this later. So basically refer to relationships, broad relationship within and between feature values, attributes, object source and aspect, structure, distribution, relation, and so which means relation of relation, right? And relation of methods, relation between models, between the outcome like an impact, the risk level, etc. So we put these two together. So that's what we call a non-IIDness. And this actually exists in either small data as well as big data. Right? So even very small data, there's an issue, this issue could be quite serious for some time, and we cannot actually ignore. But for big data, so not just volume, right? So simply, it's non-ID. So I just explained why we have. I think heterogeneity is easy to understand, but why do we have the term coupling? So I mentioned earlier that there's a work actually in the cybernetics and also in statistics. And in some other area, actually particularly talk about the couplings of models in statistics and also couplings in cybernetic system. Right. So this could refer to many things. That could be, relationship could be numerical, could be categorical, could be textual, could be mixed size, or could be syntactic, semantic. And sometimes actually this could be related to organizational, social, cultural relation, economic relation. Sometimes actually not really clear, right? For example, so when some of you guys actually sit here in this room, so what is the reasons bring you to this room actually? So is this a dependence? Is this correlation? Is this association? Right? So there are many things that actually drive your behavior, right? And that may not just be described by dependent correlation, association, which have been well quantified or formalized. Does that make sense to you? And then coupling here, and it could be like explicit, implicit, could be qualitative, quantitative, could be descriptive, could be deep, which means we can actually use a deep model to learn some of the relation we actually don't know at all, right? And So those things put together, we feel, okay, interesting. So we probably have this term. Actually, I wrote a paper just to particularly discuss, different types of, different forms of, different hierarchical and structure of coupling. So, and this actually has driven us the past few years, to revisit some of the algorithms we have developed in the community. So give you an example, like, so nowadays everyone talk about behavior. So behavior, so this is like a hard concept of behavior. It means, a behavior set consists of multiple behavior. This could be human behavior, could be robot behavior, right? So the behavior could be actor, this could be subject, could be object, and then got an operation pair. And then we know that there could be this or that relation between behaviors. And then for the, related to the actors, could be between, subject 1, subject 2, object 1, subject 2, right? And then operations as well, right? So then you come up with, something we call an intro, behavior coupling relation or behavior coupling relation. And this kind of relation, so if we look at the behavior in particular, in different kind of system, and this could, be from temporal perspective, could be from inferential or party-based perspective. And each of them actually could be further explored from many subtle areas, like a temporal relation between behaviors could be serial coupling relation, parallel relation. That could be in, synchronous or asynchronous, etc. So we have I have made a long slide, actually more than 300 pages online to talk about behavior informatics and particularly talk about different kind of behavior relations. And just one of the tutorial is Ichikai, cover this area. So just give you an example here. So I won't go detail. And so then another thing that why this, the current exploration in statistics or in some of the area, there's quite a few good papers in the relevant community you can find if you Google, use non-ID data or something. So what is our view? What is actually the real problem of non-ID learning? And we actually thought about this from many perspectives and in a much deeper way and a more comprehensive way about this non-IDness. And that could be stemmed from, particular aspect like entity and property of entity, the interaction between entities, for example, and then the learning, the system, and the context. And each of them, like the entity could be like, could be a data object, could be a data source, could be just an instance, right? Could be an attribute, could be attribute value, right? So it's depending on our focus, our target here. And then probably there will be, not only just the value, but also the distribution structure, the semantics, the logic, the linkage, and the dynamics related to property. So some of the work later, we introduce the model to actually explain this. And when we talk about interaction, so the interaction may happen with many different types and the entities or on the properties or the learner or even the outcome. So that could be like a dependence and correlation association that have been explored well. And it could be just a simply matching based type of thing, and also semantic and co-occurrence or neighborhood based distance, density, uncertainty, logic, overlapping based in the networking and connection, etc. So many of them we actually have addressed, in some of the existing algorithm or learning theory, and then the context, in the context of well, certainly this will be important, and that could be related to social, cultural, economic, aspects, and quite interesting. Essentially, so I just briefly explain here, but if you want to look for more information, explanations, and example, you can find it in some of my papers. So I have much deeper discussions there. And then the second thing, so that's is about the hierarchical. So what is the hierarchy of these non-IDs? So we actually think about from the feature value to feature and to object, and let's cover like sample instance and also like the source and the method and the measure. The measurements there could be non-IIDness there as well. And then suddenly we have multiple methods like ensemble learning, and later I will introduce algorithm there. Ensemble learning we have to consider that. And then when we talk about the value, so some of the work we'll introduce here is that for outlier detection, we actually consider the value relationship, and then combine value to attribute to object relation, right? And so we find actually the problem quite interesting, and many things we can actually rethink and actually can explore. So then, so briefly, so what is the problem? So we have like a very high level empirical observation. It could be something like that, but still the original learning problem with boundary there and three heterogeneous objects and the relationship there. And we have to respect, there's a context here, right? And these objects or whatever entity, they are heterogeneous, and they actually follow different distribution. And then the relationship between the objects and the relationship between the object and the baseline, I mean the base, the center or whatever, needed to be considered. Then this will be the objective function here, right? So objective function, when we calculate the D3 here, we have to consider actually O3 is affected by O1 and O2. So we got R13, R23, right? And then similarly for this base O will be affected by O1, O2, that is D1, D2, right? If that makes sense, right? So that's the key idea is that actually drive all the design. So we have been working in the past few years. So that's basically to explore. So how much we can do for that, and there could be hierarchical value, there could be many things we discussed just now. Just a simple projection like this actually costs us so many years of our time to think and to explore. And that's some of the preliminary outcome we want to present here for your discussion and for your advice. So related work, so I'm not going to talk about them. So you can actually find from the online website, the slides where they shared them. And so that will cover different areas, just as I mentioned. So now I move to the first case session is about non-ID data representation. So we have knowledge representation. So data representation or representation learning is becoming a big issue, and a lot of effort have been made here. So we'll particularly focus on three things here. So one is matrix learning, another is similarity learning, and then another one is embedding learning. So I just briefly introduce three pieces of work, recent work we did. So the first one is about a similarity-based representation. So this is published originally with CIPM and then with TNN, extended version. So the basic question we want to ask is that, so we go to like a very nice place actually at a very nice moment, and two person, I believe actually a lady and a woman, a lady and gentleman actually sit together there, enjoy something. So I want to ask is what happened with these two guys and why they sit there, right? And just like, if you don't mind this two girl and a boy, so why are this particular moment you sit here near to each other? This is some ridiculous question I want to ask. So I mean, from the modeling perspective, it's possible for us to actually build a model to address this kind of question, right? So essentially, this is some funny thing we try to think about, right? Okay, so and we work out. So use the information table, which means this transaction data information table. We can actually have a high-level general approach or framework. So I just presented the framework first, and now we introduce the detail, because I want to give you a high-level structure before we go to the detail. And so you have an information table. We call it standard information table, which means you go to the object scale, put attribute A1 to AJ, and then go to something else. That's going to be like different models, right? So I'm going to like classify 1, classify Q, and then you put a class label here, right? Labeled each object, right? So this is something we put together called a standard information table. So we do this for particular purpose because we want to capture the relation, And then the basic idea in this particular work is actually something simply called a pairwise, right? But the pairwise is something complicated. So for each attribute, basically, for each attribute like A2, you got different values, V12, V22, etc. And there's a relation between them. And there's like, there's a boy and a girl. There's a gender, there's a value there. And for this gender, and you want to look at the relation between them. You see, Hamming distance already there. It's a true matching, right? And boy, girl, they don't equal to each other. So it's 0. Is that right? Right? Yeah, for gender probably, but for some other attributes, you probably have to ask, really? Right. So that's something actually we have to revisit, rethink. And so that's one dimension. And then, so we know that, like, V12, V22, the relationship between them will be affected, or more or less affected by other attributes, A1 or something else, right? But for this particular example, like gender, male and female is given, right, by parents. You can't even change them, and the age may not influence, But for some other, like good reasons, they may affect this relation between these two values, right? So that means we have to consider the influence of other attributes on this, attribute value relation. So now you move from one level to another, right? So this is a value relation and then attribute relation. And then we work on ensemble or multiple class, multiple label, right? Or multi-view or multi-task, multi-source. So what is the relation between them, right? So we have to look at that before we finally explore what is the similarity between O1 and O2, right? So the object similarity, learning, so has to consider quite a complicated, interactions. But if those objects or attributes, they are heterogeneous, and then the problem will be very complicated, right? Not so simple. And if we do a clustering, we can't just use k-means. If we do a classification, we can't just simply apply k-n. Does that make sense to you? Okay, so now we go to more detail and give you a little bit more, how we design these. So we have some key concepts, so basically to capture this hierarchical pairwise coupling relation. And one is called an intro-attribute coupling. So that's basically attributes level. It's a within attributes coupling relationship, basically for attribute value, right? And second concept we call the inter-attribute coupling. That basically means the interaction between attributes. So simply, so we illustrate by this, simple information table pair. So you go to like B1, B2. So I'm going to look at the relation between B1 and B2. This is something we call the intro-couple or intro-coupling relation. And then it's got an impact on, from A1 on this B1, B2, or A3 on this B1, B2. That's called an inter and intro. And then what we needed to do is how can we capture the information from this simple data? This is quite a simple data, right? So how can we capture it? So before we do that, so if some of you would like to make yourself busy here, maybe you can this is a very simple example, right? You can take a picture. You can calculate the similarity between U1, U2, U1, U3, for example. And then later when I introduce, finally I give you some of the outcome, you see whether your outcome actually will be similar to this one, as what we did here, right? So in order to capture the relation, the information there, and we have to design something we call set information functions. And we actually design different, different types of set information function. And some of them called, basically two set here. In this particular piece of work, one is called f function or f star function, and another is called g function or g star function. So let's just forget this formula here. I'll give you an example, much easier to understand it. So this f function is that, so if given object here, like u1, u2, whatever, given object, we want to find the value on one particular attribute, like 2, right? So that's for like f2 u1. So f2 u1 will be b1, right? And f star function is to get all the values, basically the value set for all those objects on that particular attribute. For example, so attribute 2, for U1, U2, U3, so that will be B1, B1, B2, right? So basically the unique value will be B1, B2, right? But suddenly B1 got twice, got a frequency there. Right? So now we're going to leave you more information from the data here. And then another function is called a G function or G star function. That if I'm given a value, so what are the objects, right? So for example, B1 for attribute 2, you got a U1, U2, B1, B1, U1, U2. And similarly, if you are given 2 values or 3 values, I can find all the objects. So what is the purpose here? Why do we define this set information function? So the purpose actually is to calculate the similarity from the the hierarchical perspective. Is for the later for us to design some of the similarity measure, because this is a similarity-based representation. Okay, then we define this is called a coupled attribute value similarity, and that's so give for attributes J and the 2 values x and y. Sorry, we changed this. The 2 values x and y, and what is the relation or what is the similarity between x and y for these attributes? So the principle here, we think we have to consider 2 aspects. One is that, okay, within this attribute J, so we call it delta GIA. IA means the inter, is a relation or similarity between X and Y. We call it inter-coupled interaction. That's delta GIA. And another part is called inter-attribute coupled interactions or relation. That's actually delta GIE. So it's actually capture the relationship between X and Y for attributes J affected by all other attributes, basically. Right? Make sense? So that's a high level framework. But suddenly you can change the framework, right? You can change, and this dot just represents one type of integration, right? So this could be linear combination, could be like a multiply or some other, right? So it just indicates they have to be integrated in some way. So we just use a very simple way to calculate and then look at the performance. The simple way is that, okay, so for delta JIA, the relation between X and Y for J attributes, and we just get the frequency of X and Y, and then their co-occurrence in some way, and calculate this similarity in this way, right? So it's quite simple, right? So simply I see for B1, B2, for this attribute 2, then you can find this is a relation. The similarity between B1 and B2 will be 0.5. Oh yeah, simple, because you've got a 2 B1 and 2 B2 as well, right? Okay, quite simple. But suddenly you can change this similarity function. But for this inter will be very complicated, not so simple now, right? So just now we just use a simple way to calculate the inter and inter. So basically what we do is that is use a modified value distance matrix. You've got X and Y. So we want to see for the J attributes, affected by all other attributes. Something like modify this MVM, and we replace this C by what? By the other attributes will be K. So which basically means we'll get 2 sets, right? So Y is for X and other for Y, but it's conditional on all others, right? So we just calculate the distance, and that will be converted to our target here is that okay, the J's relationship affected by all other K can be derived, and we can get a formula like this. So, and when we do this, actually we can find there are 2 different kind of, between these 2 sets, there are 4 different kind of relation. That could be power set, universal set, joint set, or interaction set, right? And this actually represent, how can we calculate for these different kind of set interactions between these X and Y based, set interaction, basically. And suddenly we have to, we've got something else we want to talk about here, but we actually can prove actually that all these 4 scenarios can get the same accuracy, but the complexity is quite different. But there's something different I don't want to highlight here. And now see, how do we calculate this XY similarity for J? It's actually to consider the J affected by all K, right? Or basically conditional on all K. And then suddenly you can do different kind of combination that could be linear, and there could be combining other way, right? Okay. And then, so we get the attribute similarity. So attribute similarity for J attributes, and we have to consider the, within these attributes for inner values. Sorry, we change this again. This is the value x and y, and then for J affected by all other K, right? So we can combine them. We can use some way to combine these two parts. Right? So that's basically the attribute level. And then how about the object similarity? So finally, we get the object similarity. So for two objects, ux and uy with value x and y, right? And the similarity between them is a combination of all of those attribute level similarity that consider the inter and inter, with basically within the attributes and between attributes for J, and then sum all of them. But this could be sum, it could be other way, other aggregation way. But idea is here is basically do the pairwise, and this is quite costly, as you can think. So, but idea is that is to do the pairwise coupling, hierarchical coupling. And this now is an example. So quite simple example. And then with the technique we just introduced, so essentially what we did is that we developed a function, and we got a different kind of information function to extract. So given this information table, we can extract information from this information table by creating many different kind of information function. And then you just search this table, and then to calculate, why want to get the similarity between U2 and U3. U2 and U3, and then I can just search from the table there and then get the similarity value between U2 and U3. So in this table, so you see, if you look at U2 and U3, so I don't know whether you can get this particular figure here. But anyway, that's the idea. So it's basically so within the attributes and then between attributes, and then you aggregate for all attributes, and then you calculate, the object, the similarity for the objects. Is it clear? As I mentioned earlier, so we have to prove actually, these four kinds of, set interaction actually they are equivalent in terms of accuracy. And so actually we can do that, and also we can actually find there's one of them actually much simpler than others. So that's something from the complexity perspective, it's much simpler. So now we can use this one, and there's an algorithm we can use this to calculate, and that's quite straightforward as I just introduced just now. And then we just use this to evaluate. Just use very simple data. UCI data. It's not a big data, right? It's just a simple data, highly manipulated. And just combine these with a very typical algorithm K-modes, because we work on categorical and spectral clustering, and compare with some of the existing methods, and then see what could be the difference here we can make. So you see very simple data, UCI data, and we compare different similarity metrics, and we evaluate the different similarity in terms of a few performance indicators, like relative dissimilarity, down index, or DB index, or some dissimilarity or other, and compare with some of the technique like could be simple matching, could be occurrence frequency, could be another method called ABE, and this works well in some of the category data as demonstrated in their paper. Right? And you can see, as I mentioned earlier, and from this four dimensions value, you will find actually some of the data got quite a big difference. The variation for those data set, this one, and some of the first one, and the second one, and you will see actually quite significant. So we actually indicate that we actually have to rethink the similarity we have been used, like simple matching, timing distance, those kind of things, right? And we have to consider something else in order to do things right. And then we combine with K-modes, but basically just we don't change the K-mode process. We just replace the similarity by what we developed, and then just compare with the original one. And then you can compare with other ways, And for k-meals and spectral clustering, work on the very simple data, and then look at whether we can get some gain, right? So you will see actually some of the data set actually you can get a great gain, and some other, the improvement may not be so big, right? So but this at least indicate this problem could be quite complicated, could be interesting, if we can fully explore, and sometimes we probably have to explore them. This makes sense to you. So that's basically the first example, so called a similarity-based representation. So the second example, so I'm going to introduce the matrix learning. But this is much more complicated compared to the previous one in some way. So basically, the focus on matrix. So this paper did is just still under review in TBD at the moment, and the idea is the same. So given a very simple table here, so by the way, we still work on the categorical data because the numerical data has been explored quite well. We've got a lot of distance definitions, and the categorical hasn't been explored quite well, and it's easily to get into a wrong space actually. So as far as we experienced, so that's why we particularly focus on this categorical, and then suddenly the integration, the mixed data as well. And so if you just look at this simple table, so if you just look at the commitment of the students or whoever in the class, so if you look at some of them got a high commitment or low level commitment, and if you just compare from the commitment perspective, it's probably hard to really for us to get a good picture about their similarity or their difference, right? And we just use Hamming or frequency based. We actually see we need to consider more than that. So, and the model is like this. So when we have the basic idea is that, so when we have heterogeneous data, so which means the data actually is different, right? It's a follow different distribution and different data, right? And that's the original data, but the categorical. So in the categorical space, so we want to have a transformation to our embedding space. So, and in this embedding space, this can better represent the data, basically. So I have to find a good transformer to do the transformation, right? And then we build a matrix, function. The matrix function on top of this embedding space, and then to convert further from this very original space to another space called a matrix space, or distance space. In this distance space, we can better actually understand the data characteristic. That's basically, especially we understand the data heterogeneity and the data interactions. Right? So that's the idea. But from the learning perspective, we want this, could be quite similar. We get an approximate, outcome that actually can approximate, the original, things. Right? So that's a high level idea. That's a task. Yeah, basically, I just explained. But rather than calculate the distance between OI and OJ, so here we actually convert to another problem in this distance space to calculate the distance between two vector xi and xj, right? In this learned matrix space, basically. So matrix, which means you need to satisfy those properties of matrix, basically, right? So how do we make it? And we create a framework called heterogeneous matrix learning with hierarchical coupling. So the idea like that. So given the categorical data, and we actually look at the hierarchical coupling relation. And so one is called the inter-attribute coupling relation, which means something I just explained all out, like attribute relation, attribute value relation, and then another coupling relation. And the third one is that for this particular example, we actually incorporate the side information of label. So we have attribute class coupling relation. So one task, the first task we have to do is to create a similarity function for all three different types of coupling relation, right? Because they are heterogeneous, they are different. And then for so they are heterogeneous, we want to convert to a kernel function, and then so that we can have the matrix property applied to them, we can do better aggregation and other reasons, right? So so we have the heterogeneous kernel for them to be integrated, right? And then further, when we get this learned kernel space and this tree space, we actually learn the heterogeneity, and we want to integrate them to build a distance space, that's a matrix space. In the matrix space, we can solve the problem and create an objective function, things like that. Right? So that's a high-level idea. So, and in doing this, we actually incorporate the hypothesis, and that could be could represent a prior or implicit relationship there, or there some of the assumption. And also the such information could be related to observed information like the key, the class label and some other like ordinary information, etc. And incorporate that and to solve the problem more easily. So how can we do that? So we see we have hierarchical coupling learning. So learn the value to attribute and to class coupling relation. So look at it from bottom to up. So we have these three: the attribute to class coupling, and inter-attribute coupling, and intra-attribute coupling. And for this case, we actually use a different way to do that. So certainly there are many different ways we can create. Just use some simple way to calculate and see whether this could make a difference or make a significant difference. And for intra-attributes, we just consider, we still have to develop many information function here as well, for the G function or P function here. And this G function capture, for a given value of I attributes, for the J, one of the objects here, and then for the I objects for the J attributes, so we can get the value frequency and then divided by the number of objects, and then roughly you can get the rate to measure this value importance in this particular case, right? And but certainly you can calculate in other way, right? And also the inter-attributes, inter-attribute coupling. So this will be much more complicated. Actually, you consider the Vij conditional all other value, which means the other values actually have impact on this Vij is measured by this inter-attribute coupling. Make sense? And then the last one is attribute class coupling. So it's to capture. So basically we have class, right? So for the value, what's the relationship between the class, like class label C1, and this particular value, Vij, right? So calculate the probability, basically conditional probability in the data, and for this particular class C1 for this value, right? So that's basically to capture the different type of coupling relation. And then another task is a heterogeneity learning, is to learn the heterogeneity. So what we did that we actually convert the earlier outcome to a kernel space, and this is actually a kernel matrix but high dimensional somehow. So we have this diagonal represent the similarity for the intro basically, and then the interaction between the attributes basically represent other attributes in this kernel space. So suddenly you can have different way to do the kernel and to have different kernel. When you have different kernel, in general manner, this is a kernel space, isn't it? Right? So you can have many different kernel depending on how many kernel function you use, right? And you can have different kernel here in this big one, right? So then we have to do a transformation to find a transformation the function here, matrix TP, and to transfer this kernel to another space. We get the P transfer the kernel space, and so that we can later do the distance calculation. So that's a purpose here, right? So then furthermore to the matrix learning. So that's now we move to the distance space, and we for the transfer matrix and the we have to build a positive semi-definite matrix for this TP, and our goal here is simply to calculate the the idea for two objects. And that has to consider the idea for different kernel. You got a P, transport kernel, you got a, other, right? So, and that could be, aggregated, for all the NK kernels you actually create, right? Make sense? Right? So this folder you can derive to this one. So this one actually essentially can be represented by, a matrix that's for the weight matrix, and the weight matrix, this could be converted to something like this. It's a diagonal essentially, right? But that's just something, for the more detail, right? And this key idea there, and it could be for the extent, related to each particular kernel. So we have NK kernels, right? Make sense? Right? And then the learning function here would be something like that. Okay, so we have to work out, select the right kernel with some of parameter number, and so that it can satisfy the matrix function as a base, as well as force a distance, and then integrate and then project a matrix space. Well, that doesn't make a difference, and that's what we want to see. So that's the first method we create, and that's the method created by all other team pair, including the Hamming distance. It's a simple one. So if we compare and work on probably 24 also data objects, and you can see actually the improvement very significant, about a 15% improvement, right? So almost, the algorithm we create, beat almost everyone else. Some of them, get equal outcomes, some are simple data there. Right? So it seems like this is quite significant, right? And even for, by the way, the data here is actually quite simple, right? So, which again indicate that, so consider the, complex relation and heterogeneity, respect that actually quite important. So that's the representation quality. Let's actually look at use some of the epsilon gamma theory and to quantify, the performance and look at these actually very significant. There's a theory there for some other people's work actually. So it's quite a significant, improvement, quite a significant outcome. Demonstrate here this is our method compared to the existing. And also we incorporate this into classification. Let's just simply incorporate the similarity, the matrix we build into KNN, and then to calculate, a new KNN, the performance, the F score. And we actually created two versions. One is just simply consider the hierarchical coupling, ignore the heterogeneity, and another one actually is consider is basically non-ID, right? So this one is just consider the relation. So you can see actually the more non-ID actually is improved, on top of this, this hierarchical complex relation based, and all improvement actually quite significant. So this once again indicate actually quite important for us to do that. And we further integrate this framework into logical regression, random forest, and SVM as well to look at the F score. So if you look at the outcome here, the mean and standard deviation, for our framework based on logical regression, and the improvement very high, actually it's 12%. And further you look at this random forest is 9% improvement, and even for SVM we can do more than 3% improvement as well. Right? So this is probably shows that actually quite important sometimes for us to explore. Even the data is quite simple. And then we look at this method, whether this is quite scalable, and look at the interactive, especially the attributes, dimensionality. Look at it converges very quickly, actually, and the train loss and the loss value, so just so quickly converge. And another aspect to look at the scalability is to look at, okay, so we have a few components in this design. We have one component do the transformation, another is to calculate the complex relationship, and there's another one is a heterogeneity. So you look at the specific components, here. So look at this one, like actually the specific the heterogeneity is quite actually linear to the dimensionality and the number of objects and the maximum number of values in all the attributes in a data set, right? And the dimensionality could be like 200 in the case, and the hierarchical coupling relation learning actually costs a lot of time, and that is understandable because here, take a quite a sophisticated way to calculate that, right? And that's the overall. So basically, the hierarchical coupling relation learning actually, costs most of the time. Actually, heterogeneous learning in this design actually shows much less, significant compared to that one. And then we look at stability. So as we can see from here, so there's one parameter in our algorithm, this framework proposed, is a lambda. And with the lambda is not very big actually. You see here something like less than 10 or something like that. You will see actually quite stable, right? But then when we move bigger, the lambda is bigger, so it's not so good. But in terms of the theoretical and this empirical analysis, actually, you can have a good lambda to control the framework and make it stable. So that's basically the second piece of work to actually consider the heterogeneity and the complex hierarchical relation in the learning. But in this example, different from the first one. First one we actually work on the clustering, and this one actually work on the classification. And both examples shows actually importance of considering this non-ID. But sadly, as we can see, there are huge opportunity because the way to calculate, the value and the attributes, and some other relation and heterogeneity could be quite different, and that could affect the outcome. So then the next piece of work is about the embedding-based representation. And this is just a recent work, actually next week in Melbourne, in Australia, the EasyCut. And it's about to incorporate embedding into so the still work on the categorical data because as I mentioned earlier, not much result in this area in the categorical data learning. And simple thing like if we look at so you got just a simple two-dimension, you got occupation and education of a few 5 people. If we just look at them, we find you got a professor. Most of the professor scientists got a PhD. Is that true? Right? Probably. Right? And engineer, you don't need a PhD. Nowadays probably different, right? So even engineer got a high pay, need a PhD maybe as data scientist or data engineer. Anyway, so look at here is that we find actually there's a hierarchical thing. There's a different granularity. You got a master and you got a PhD. And got a different type here as well. So the idea here is that so whether there's like value clustering, which means that could cover these values, not just one dimension, could be multiple dimension, and then whether there's a relation between the value clusters. Now, so this is further move to another space to think about this problem. Right? So this is representation for categorical data, particularly like one hot, a lot of people use it, and IDF for text, right? For example, and then other work like pairwise is another way as well. So and this paper actually proposed a framework called something like coupled unsupervised representation framework. Now actually we extend this to for clustering as well as for outlier detection as well. But here we just report the outcome for the clustering. So the idea is simply like this. So we have information table is categorical, and we have different coupling functions to map this information, to extract the information from the table from many different perspectives to learn the value relationship basically, and then further we do the value-to-value relation analysis is to create something called a value clustering. Right? So we do the clustering. So you can use k-means. We actually use k-means on top of the values, created from this low level. So basically, we get the value-to-value matrix. So You do the k-means clustering on top of the value matrix, and then we can get a value cluster. Right? And then if you use different ways to do that, then you get a different, value cluster matrix. If you work on different granularity, which means like a PhD or master, work on different granularity, you actually get a different value cluster matrix as well. And then we can further look at their interaction, the relationship between, those value cluster matrix, right? And finally, we can embed them, or we can concatenate them into a bigger representation, right? And then use that representation to create a new objective function for clustering. So that's what we call the embedding. Basically, this will just focus on the embedding. It's to extract the information from the very low level information table in terms of the value interactions by different function to get the value matrix. And when we get the value matrix, you can have multiple matrices, and this matrix we can apply the clustering and to generate the value cluster. So it's high level on top of the value, right? And then we can concatenate them to do the representation. So this case is different from the previous work we did, and here basically just focus on value, but do the hierarchical and do from the embedding perspective, not from the similarity perspective. Right? It's different from the other work, and so give you a little bit more detail, like so we can have like a co-occurrence based value inference matrix, and the inference means so you have a value inferenced by another. So for example, we can have a coupling function like this, good two values, vi and vj, and vi and vj we know. So there's a vi impact on this vj, right? So there's got a function there for this particular feature, and value i and j, f feature, right? So then you can actually calculate the similarity or sorry, in this case not really similarity, the embedding based on this coupling function to get all the value interactions, right, for the whole population, right, but based on the occurrence. And we can also have other coupling function to to consider the vi and vj relationship in terms of their co-occurrence, right? So basically means that vi and vj is a joint probability condition on this vi, and that's actually consider their basically their co-occurrence. And then we can build matrix we call it value inference matrix based on this co-occurrence, basically. But certainly there are different ways to calculate the interaction between values, right? And you can have different coupling function to capture the information. So the key here is to capture the information between values as much as possible and as powerful as possible. We can do that, and we can actually get more. And then we can use this just incorporate into k-means and some other, and then do it. But certainly from the detail perspective, it's not so simple. We have to work out many other things. For example, so how to get the value cluster and how to tune the k-means, for example, and on a different granularity. So I will ignore the detail. I just give you the key outcome here. And example here. So we got the data, just the user data again. So we just always use a simple data, right? So you use a very simple data and see whether we need a more powerful technique to work on those simple data. So you got the number of objects and the number of values, and there's one thing we call FCI, is a frequency, is called frequency. So I think we've got something. Yeah. Okay. So it's basically a feature correlation, all right? So there's one of a particular indicator we actually calculate to measure the average correlation strength between the features, basically. And then we actually have our model, our framework to do the embedding, and then compare with the 0, 1 and 0, 1 with a PCA, and then with IDF. And see, if you look at the p-value with 90% confidence level, you find actually quite a significant improvement compared to that. It's a very big improvement there, right? So this shows actually this kind of thing actually quite important, right? And we further compare with other similarity measure, and this is the standard of the art similarity measures compared to ours, right? And we have another one called a value clustering index. This value clustering index actually is the average of the maximum non-overlapping ratio between the value sets. And so this is an indicator to measure the complexity. And from the result here you see here, actually very significant as well, right? So this once again actually shows the importance of doing this or the value of doing this. And further we do the sensitivity test in terms of some of the parameters. This basically details. I've got two parameters, alpha and beta in this design, but I didn't give you the formula earlier. So basically, see this is quite stable here. It's not so sensitive. So performance is quite stable in terms of the parameter and also the scalability. So look at the scalability. This CDE is ours actually. This is CDE and this one. So in terms of dimensionality, when we move to 400 attributes as data with 400 attributes, it's quite costly as well. And there are some very simple ways is probably insensitive to the dimensionality, but most of the method will be very sensitive to the dimensionality anyway. So ours is sensitive as well. So that's basically this part of the work. I can report another way to do the embedding, but just consider some very simple aspect to the embedding and see whether we can improve. And we actually also extend this for outlier detection, but that's in another journal paper. So that's the part. So in Australia, you have opportunity to go to some very nice place to see something quite impressive, right? Okay. And then I just probably just quickly go through the ensemble, because so incorporating this idea to the ensemble. Just realize that it's very timing here. So the ensemble, so we know it's actually you got a so I have diagram here. So basically we have to build like a base class clustering, the models, and then we aggregate the base clustering, and then we do the post analysis to get the clustering outcome. That's basically the process. And so typically, if you use ensemble, sometimes we say, okay, got 3 objects, U2, U3, U10, and use a different clustering method, 4 clustering method to get a different label, right? So the inconsistency between the labeling and the similarity, actually U2, U3, each pair they are actually just you use a traditional way, they are similar. So what is the problem here, right? So the problem we think here actually is we have to consider a better way to measure the similarity between many aspects, So I just use this one to illustrate the motivation here that so you have 2 objects U1 and U2, use different clustering, you get a different label there. And a different label, and so we have to think about, okay, so what is the relationship between these 2 labels within one clustering? Like for clustering 1, what is the relation between class label 1 and 2, and similarly for clustering 4, alpha and beta, and A and B, is this one level. The second is that, okay, is there any interaction between the clustering, right? Like between clustering 1 and clustering 2, and clustering 1 and clustering 4. And before we actually calculate the similarity between U2 and U3, right? So that's basically the idea behind, right? So the hierarchical coupling. So then we actually define some and measure, try to capture, represent the hierarchical coupling relation. So one is for clustering coupling, another is object, and another one is integrated. So I'll give you the high-level idea here is that, okay, so within each base clustering, so we need to measure the interaction between the cluster we obtained in this clustering, right? And then between the clustering, so we can measure their interactions as well, right? And similarly, we can do this for the objects. For one object, the attributes, the values, we can calculate their similarity, called intro objects. And then between objects, we can do that as well. And we have to when we do the clustering, apply those different clustering methods on those objects, and we have to do the consensus building and to integrate them, aggregate them. So that's basically get the final outcome, right? So that's the process. And how do we do that? So so because timing issue, I probably just very quickly will give you too much detail here. The very high level idea is that, okay, so we actually have to calculate the intro couplings of base clustering, which means within each base clustering, we actually consider the class label frequency distribution, right? And then the second part is that we consider the between, the base clustering is actually the label co-occurrence dependence, which means we actually need to grab the object and use the object to look at their label co-occurrence. So that's the basic idea. So then that's the details. So I will just ignore because we have many other content there to introduce. So then we can, like for this example, so for 3 clustering method, they got different label. Just from this one, you get a label, clustering label table, and based on this label, we can calculate the similarity within this clustering, right? And also, basically between this cluster as well, and then between these two classes, like this 4 and 1, right? And or between them, right? So you can get all the similarity, between the clusters and clustering as well, right? So that's one part, and second part is about objects. And object we can use the previous way, we introduced all that, but this is considered, from the clustering label perspective. And I just ignore the detail here. If you are interested in, you can look at some of the paper. And then the integration. So integration, there are different ways to integrate. So we need to design some of the algorithms to do that. And in doing that, it's not so simple as well, because we have to consider, for a given object. So basically, there are 2 ways. One way is that so we use a clustering to do the integration. Another is to use the object to do the integration. So basically, there are different ways to do that. So I just ignore the detail here. So just give you some of the outcome here, and compare with some of the clustering method, EM, QMI, and PD. And so this is our method. You see that actually the accuracy for the very simple data, some of them improve quite a lot, some of them not so much, but basically, you can see the improvement there, right? And also use different ways to do that's basically clustering-based integration. And when we do this object-based integration, but consider their interactions, we actually can see compare with existing method, and these 2 actually are our method. By consider the intro objects and the class, the coupling and hierarchical as well. There's 2 different scenarios. You can look at actually in most cases you can get better outcome. Right? So in the simple UCI data. Right? So and then we can do the class-based calculation for the accuracy, NMI, and combined similarity index. And for the look at, so like this case, pretty much can beat all the existing method. That's for AC and for NMI, similarly, consistently for combined similarity, and improvement quite significant somewhat. And so this is another piece of work actually shows quite important. Sometimes we have to consider even for very simple data. So here I always use a very simple data to illustrate actually the importance. So now I move to another piece of work related to recommender system. So the recommender system, certainly there are a lot of things we can do, and here we just illustrate maybe 2 pieces of work here. So the first one is, before I introduce the 2 pieces, specific piece of work, actually I have some thinking about the framework of recommender system, and wrote a paper actually to talk about a non-ID recommender system, and just share with you guys, see whether it makes sense. So in the current recommender system, so what we usually, the problem we usually see actually is something like you find a duplicated recommendation. Something, I purchased some book and then recommend, same book to me. I put the book on data science, another book recommended me. I don't need it, right? It's duplicated. And irrelevant, so pushed, because previously it's like pull. So what I need, I just go to search, right? Now it's all pushed, Doesn't matter whether you like or not. It's, but often you see something irrelevant. And then another one is missing, right? Missing something. What I need actually is not there, right? And falsified is even bad. You got to fake information there, right? And now it's become a big issue. And this is the information, the systematic view for the information related to a recombinant system. And basically there are five key information source behind here. And so one is here is that, okay, usually what we have is that it's a rating table, right? It's basically users put a grade on the items or products, right? So you can have like a 4 score for item or other score. So this is basically the rating table, right? And then there's another one is called a user table, user information table, and that actually includes the user information. There's another one is called item information table, is consider all item properties, right? And then there's another table, mostly probably implicit interaction between the attributes in the item table and attributes in the user table. For example, so in the user table, we've got one attribute is city, and in the item table, we've got an attribute is the price. And the interaction between city and price, then you can have the CP. But what is the CP? How do we model CP? Right? This could be a very interesting question to ask, to think. Right? And this could be latent, could be something like hidden, could be something explicit. Explicit may be something like people in city may be sensitive to price of property because very expensive property there, right? And so there could be like explicit relation between city and price. There could be implicit relation between city and price. So this bit, each element here, each entry here could be quite complicated. May not be so simple, if that makes sense to you, right? And so what is the wheel here? So, sorry, by the way, so there's another thing I didn't mention here. There's another aspect is the environment, the context, right? So if you build a recombinant house in Australia, in Sydney, or you build a recombinant house here, I think it will be very different because the environment actually quite different. So in Sydney, you will say, oh, okay, your house is 3 million. People say, oh yeah, 3 million now is probably common now. But here we talk about 3 million house. So really? So are you kidding, right? So it's the environment quite important, right? So that's a wheel here. So it's non-IID here is that, so what we believe at is in each table here, so we got some of the areas, right? So in the rating table, so like, just for this dimension, like for item 1, there's a 5, 4, 4 rating. So what's the relation between 5 and 4, 4 and 4, 5 and 4 here? And similarly for user 1, what's the relation between the rating of user 1 given on different items, basically? But we know actually in general, there should be some relation there, right? But how do we learn that? And this relation could be implicit, could be explicit, right? And further, so you look at the item table similarly. So you go to the price, different price. Is there a relation between the price 100 and 800 for 2 items? Is there a relation between the two attributes like C1 and C16, which means you've got a category and a subcategory. Certainly we know there's a relation there. But how can we learn the relation within one dimension and between the dimensions? Basically, there's a similar idea as we mentioned before. And similarly for item, you got this kind of interaction. Before we talk about the user relation like U1, U2, U2, U3, and similar for the item as well, right? And this field we just mentioned, this could be like really very sophisticated, and each of these elements could be high dimensional, could be a big matrix there. Right? How do we learn that? But before we talk about that, this is quite complex. So I don't think very much work has been done in this field in this area in the recombinant system. So I discussed with some of the experts in this area, and so quite complicated but very important. But so really the simple question to ask is that, so why user 1 could rate 5 on item 1? Why? So how can we build a model actually can learn the complex drivers, driving force behind. So why this is 5, right? So we can somehow believe that, okay, this 5 actually is driven by the semantic thing or, subjective, things like, oh, user 1, I just put a 5 there. But there are more like a rational thing behind that could be related to this item table, related to item 1's properties, and also user 1's properties. So which means this could be more rational drivers from the user and item perspective, and also more importantly their interaction, right? It's really the interaction between the user's attributes and item attribute that probably will be the key drivers why user 1 put a rate 5 on I1. Does that make sense? Certainly within certain kind of context, which means we have to learn this context as well. So that's something I call the non-ID. I call the non-ID means in the Roman system. So if we summarize here, let's see, in this very simple rating table, there's a non-ID there. That's basically represent explicit user item non-IDness. But some people say, oh no, it's not just explicit, it's actually implicit, because I can use MF. MF is a way to represent this explicit relation. And then there's a user non-ID, I think everyone agree now. So item non-IDness as well, and this implicit user item interaction. But actually not only just implicit, there's explicit as well. Like if I click, if user 1 click item 1 many times, and that actually indicate, and and there may be other like give comments, there's going to be explicit as well. So these three aspects actually form drivers on this rating dynamics in certain contexts, and that's the environment, and that's certainly also non-ID if you look at it from that perspective. So then many people can be generated, right? So I just play with many things and got different concepts like cross-domain transfer and group-based and session-based, etc., etc. So it's got different generation of Raman system there, and that's beyond this talk. So I just ignore this. And so just move to the one example here is that, let's see. So further a little bit, so if some of you work in this area like for heterogeneity, that's basically non-identical distribution. So that heterogeneity could be on the user's items, domain, and group, etc. And so my group and some of students do papers in this area. Like recently, two papers with ASM transaction information system on the cross-domain and integrate the heterogeneity into the recommendation system for code star, etc. And so another is that, okay, this non-independency, and or put another way, coupling relation, right? Between or within attributes, items, and domains, and other information. There are quite a few papers there as well. And for considering the social inference, like with ASM information system, and group-based with the triple AI, and some other, the session-based with ZCL, EGK, etc., and cross-domain, and with and some other with ASM transaction information system. So I just use a very simple example here, probably before we have break. And very simple example is that, so in MF, probably most probably used model is MF, isn't it, in the Raman system. So think about the MF. So it's quite simple. I think everyone knows here probably. So you got a rating table there. So you got some missing value. So got the people here U1 to UN and put a rating pair on the items, and then in order to estimate the missing rating, so we can have mathematical things called a matrix factorization, the theory, and help us. So what we do is that decompose this to two latent matrices, one to represent the user's latent attributes. That's called a P, usually P matrix. Another is Q matrix to represent the items, latent attributes, right? And then we can solve the optimization problem, as long as we can, approximate this to this rating and to decompose it and find the optimal decomposition, and then we can solve this problem, right? Very beautiful, right? Simple and easy to understand. But if the same table here, and just for the same, let's see, for the same issue like a house, right? So you got a house like an M house and N people, and do the rating on each of the house. But with, we do the two tests, two trials. One trial we did in Sydney, in Australia. Another trial we just do it here, right? By you guys here. But the condition is that, okay, the rating will be exactly the same, okay? But by different people, different house. Or even you can do that, for the same house, by different people, but rating will be exactly the same. My question is that, if we use MF, do the decomposition, would we get the same outcome? Yes or no? Who would like to put your hands up? Yes? Or no? So is the question clear? Right? So rating is exactly the same. And we use the same MF method. Okay? We just use the MF method, but different people do the rating. And the house could be the same even. Could be different, could be the same. Let's put this case just the same house. Right? So with this afternoon, don't do anything, let's go up, right? Find a few nice house and do the rating. But one group actually people from one country, another actually group by another group of people. But rating will be the same. So when you do the decomposition and you get the same outcome, you will get the same, right? Without any doubt, will be same. Why? Because this is a mathematical problem, right? So will be same. Of course, they say, oh, yeah, I can set a different negative for the value. No, that's different thing. But if just this one, you will get the same. But does this make sense? That's something we have to ask. Right? So if you have like just change this, it's still the same rating, but the problem is actually different. Why is that? Okay, so a group of children in Australia, because I'm in Australia, so I use the example in Australia, okay? So a group of children, they vote the books, right? But they go to the rating table like this. But there's another table, exactly the same rating, but did by, let's just do some like, sometimes we go to the, some animal, smart animal, right? And they do the voting on some of the games, sports, right? And they get the same outcome. And then we decompose it, will we get the same outcome as well? We'll get the same outcome. Does that make sense? Really, that's a question to ask. No, it doesn't make sense, right? And we have to understand the reason, why this, and what is the more reasonable way to work it out. And that's really the motivation behind. So because, essentially, this is just, when you forget this, the you and away, essentially this is a mathematical problem. That's why you always get the same outcome, and that's why it doesn't really make much sense in the reality, right? And that's why we cause a problem somehow, the recommendation problem. So how do we do that? It's quite simple, and we can use the way I just introduced earlier and see. Okay, so if you got a group of people, right? So sorry, the group of people, and if this, we just have to incorporate the the users' information here, their attributes and their value, and we have to just incorporate their non-ID in this user table and also the item table, right? We just have to learn them, right? If we can learn them, what does that mean? It actually means we have to, just like this table, what does that mean? So it means like, this guy U1 put 5 on I1, and we have to consider the real driver here, right? And similarly for this one, we have to consider. So we have to consider, the complex, whatever relation and heterogeneity in this table, their influence on this 5 rating. And similarly, this one, and more importantly, is the interaction between these attributes and these attributes. That will be this part, right? Does that make sense? Right? So in doing that, so suddenly I think there are many different ways to do it. So, so just a very simple way. So idea is like this, right? So you just follow the previous idea and just do it. And then we can calculate, the user, relation between UI and UG, the relationship, the similarity basically. And you can calculate for, each attribute, the similarity, all between the values for that key attributes. And then the influence of other attributes on this, value, right? And then you can, integrate them together. It's just simple as we did before. And similarly for item, so you can calculate, you can build another similarity measure to measure, the price relation or the category relation in the previous example, and the influence between the attributes as well, and you get, in order to get, two item similarity. Now, so when we do this, we actually consider the data, actually, right? We involve the data. We involve the data characteristic into this. But how do we change it? So now that's a casing. So we go to the basic, the classic, the very fundamental, MF. So do the rating, you get a P and Q. And so what do we change here is that we have to change the objective function, right? So that's so this bit, these two parts actually just the classic MF in their objective function. To do the estimation, you want the estimation to be as close as possible to the rate, to the real rating, right? And then you have two penalty functions. So for the latent matrix generated for item and for user, right? So that's basically the traditional objective function. So we can change actually. So we change is that, okay, we see the user here, U, is affected by V. And we have to incorporate the real data, which means U and V, based on the user information table, there are interactions between U and V, right? So in order to select this U, so you can't just simply do that. So, right? So you can't simply just decompose it. We have to consider the influence, from the data perspective, and this is latent based, right? It's basically latent. And similarly, we can do that for the item, right? So you go to the items and item interaction, item similarity, and incorporate that into this Q matrix, and in order to make this Q and P, reflect the real problem on the line. Does that make sense? Right? Okay? Right? So this is two bar. And suddenly, when we do that, we have to incorporate some trick, like do the neighborhood or something like that, in order to solve the problem there. And then you just do the greedy descent to do the optimization to find it. Right? And then there are many different ways to change this MF. Right? There's one paper by my team, and in this KDD, and actually he will present later. And he actually also MF, but incorporate the trajectory invasion into the MF and change it, called a discrete, MF, right? So there are many different ways to change it, but the key idea is how can we get the data information and the non-ID characteristic, learning the data to change, incorporate this into the, MF. So that's the key idea. So then we compare with the basic probabilistic matrix factorization. We compare with the single value, the SVD basically factorization. We compare with the social relation, but implicit social relation based models, MF, and also we particularly compare with different similarity, which means whether the similarity also make difference, right? So we just test the different similarity, Pearson correlation, cosine, Jakarta coefficient, and we change the MF to see whether this will make sense, right? And we just use a public data like moving length, 1 million, and book crossing, but they don't have much, really don't have much the user and the IT information, so it's very limited. And even with a very limited, user and IT information, we want to see whether we can make some improvement. Surprisingly, and not surprisingly, you can see how, probabilistic MF, that's basic information, implicit social relation based MF, and SVD based, and also this R is incorporating the what we call the coupling relation. Here, in this case, we actually we didn't consider the heterogeneity, just consider the hierarchical relationship there. And you see actually improvement. Some of the improvement just so huge, right? This is the error rate, right? So MAE and RMSE. And you see some of them actually is 70%. Some of them like 60%, 40%, 60%, 60%. And some of them, unfortunately, still very minor. And you have to tune the parameter, right? Okay. But this actually shows so significant to do this in the Rwanda system, and that can actually change